Hello, I will be presenting on welding processes, a cornerstone of modern manufacturing. Welding is not just about joining metals, it's about creating permanent, high-strength bonds that enable everything from the construction of skyscrapers to spacecrafts. In this presentation, I will explore the physics behind welding, the major categories of welding processes, their advantages and limitations, and where they are applied in industry. By the end, I hope you'll have gained a clearer understanding of welding processes and why engineers select one method over another. Welding is defined as a permanent joining process that creates metallurgical bonds. Unlike mechanical fastening, which relies on bolts or rivets, welding fuses materials together at the atomic level. There are two broad categories of welding: fusion welding, where the base metals are melted, and solid-state welding, where bonding occurs without melting. Welding is essential in industries like automotive, aerospace, construction, and electronics. For example, aircraft fuselages rely on lightweight welded structures, while automotive frames use welding to reduce weight compared to bolted assemblies. The key advantage is eliminating stress concentrations while also achieving a seamless joint. To ensure proper safety and establish welding standards, the American Welding Society regulates all industrial welding in the country. The physics of welding revolves around heat transfer and fluid dynamics theory. Heat is transferred via conduction from the welding torch into the base metal, convection within the molten weld pool, and radiation from the arc or flame. The weld pool behaves like a small lake, influenced by gravity, arc pressure, and surface tension gradients, which is known as the Marangoni effect. Cooling rate is critical, where rapid cooling produces fine grains which are strong but brittle, while slower cooling yields ductile but weaker coarse grains. Equations help quantify this, where the heat input is Q equals VI dot T and power density is P equals VI over A. Engineers must also consider the heat affected zone, which often has different mechanical properties than the base metal. Welding processes can be classified by their energy source. Electrical energy powers arc welding processes like stick, MIG, and TIG welding. Chemical energy comes from the combustion of fuel and oxidizer, known as oxy-fuel welding. Mechanical energy is used in friction and ultrasonic welding, where motion or vibration generates enough heat to melt the metal. Radiative energy is harnessed in advanced processes like laser and electron beam welding. Each power source affects penetration depth, precision, cost, and portability. For instance, electrical arc welding is versatile and widely used, while radiative sources offer extreme precision but require expensive and complex equipment. Arc welding uses an electric arc between an electrode and the workpiece to generate temperatures between 5,000 and 20,000 degrees Celsius. This melts the base metal and often a filler electrode, creating a very strong joint. Essential components include a power source, electrode, and shielding to protect the molten pool. Arc welding is the backbone of industrial welding, used in construction, pipelines, and shipbuilding. Its versatility and strength make it the most widely applied category of welding process. Shielded metal arc welding, commonly called stick welding, is a manual process using a flux-coated consumable electrode. The flux decomposes to produce shielding gas and slag, protecting the molten pool from contamination. Its advantages include simplicity, portability, and its low cost. However, its limitations are its slower deposition rates, the need for slag removal, and reliance on operator skill. Shielded metal arc welding is widely used in structural steel, pipelines, and field repairs where portability is critical. It remains one of the most versatile welding methods despite these limitations. Gas metal arc welding, also known as MIG welding, uses a continuous wire electrode fed through a torch with shielding gases applied like argon, carbon dioxide, or helium. Its advantages include high deposition rates, adaptability to automation, and minimal slag. Its limitations are sensitivity to wind, which can disperse the shielding gases, and higher equipment costs. Gas metal arc welding is ideal for automotive manufacturing and robotics, where speed and automation are essential. It's a clean process that produces high-quality welds in controlled environments. Gas tungsten arc welding, also known as TIG welding, uses a non-consumable tungsten electrode with an optional filler rod for thicker joints. It produces clean and precise welds with excellent control. Its advantages include high quality, no spatter, and suitability for thin materials. Its limitations are its slower speed, higher costs, and the need for skilled operators. Gas tungsten arc welding is critical in aerospace and stainless steel fabrication, where precision and weld integrity are paramount. It's the process of choice for critical joints requiring defect-free welds. Submerged arc welding involves an electric arc submerged beneath a granular flux layer. The flux shields the weld, stabilizes the arc, and can add alloying elements. Its advantages include high deposition rates, deep penetration, and minimal fumes. Its limitations are that it's restricted to flat or horizontal positions and is less versatile than other methods. Submerged arc welding is widely used in shipbuilding, pressure vessels, and large structural components where efficiency and strength are necessary. Resistance welding generates heat through electrical resistance at the joint interface, with pressure applied during heating to forge the bond. No filler metal or shielding gas is required, making it clean and efficient. It's commonly used for sheet metal joining in mass production applications, especially in automotive assembly lines. The simplicity and speed of resistance welding make it ideal for high-volume manufacturing. Spot welding uses electrodes to clamp sheets or thin objects together while current passes through them. This forms a weld nugget at the interface. Its advantages include its speed, cleanliness, and repeatability. Its limitations are that it's only suitable for lap joints and has thickness restrictions. Spot welding is ubiquitous in automotive body panels and appliances. Those small circular marks on car doors are spot welds, a testament to its widespread use. Seam welding is similar to spot welding, but uses rotating wheel electrodes to create continuous welds. It produces leak-proof joints, making it ideal for fuel tanks, radiators, and sealed containers. Its advantages include strong, continuous welds and high speeds. Its limitations are that it's mainly suitable for thin sheets and requires very specialized equipment. Seam welding is like stitching metal sheets together, ensuring durability and leak resistance. Oxy-fuel welding relies on the combustion of fuel gases and oxygen to produce a flame that melts the base metal and filler rod. Flame types include neutral, oxidizing, and carburizing, each affecting the weld's quality. In oxy-fuel welding, flame control is critical. Too oxidizing can cause brittleness, while too carburizing can introduce carbon contamination into the welds. Oxy-fuel welding is a versatile and portable welding process used in repair work and smaller scale fabrication applications. Oxyacetylene welding is the most common type of oxy-fuel welding, where acetylene is the fuel. It uses an acetylene and oxygen mixture to produce a flame of around 3,500 degrees Celsius. Equipment that is required is a torch, regulators, hoses, and safety gear. The advantages of this welding process are its portability, versatility, and relatively low cost. The limitations of this are its relatively slower speeds, less precision, and greater distortion compared to more modern welding methods. It's widely used in repair shops, art metalwork, and small-scale fabrication where portability and simplicity are required. Laser beam welding uses concentrated light energy to melt materials together. This achieves a high degree of precision, deep penetration, and low distortion. Electron beam welding uses a high-energy electron beam inside of a vacuum, which achieves an extreme energy density. Both processes allow welding of dissimilar materials and are used in aerospace, defense, and nuclear applications. They represent advanced welding technologies that offer unmatched precision. However, they require specialized equipment and environments that are difficult to attain and make them unsuited for most welding jobs. Solid-state welding achieves bonding without melting, using mechanisms like pressure, vibration, or diffusion, rather than high temperatures. Clean surfaces and precise control are essential for this welding process. Examples of this include friction welding, ultrasonic welding, and diffusion bonding. Many applications of this welding process are found in aerospace and electronics, where distortion must be minimized and joint integrity is critical. Solid-state processes expand the possibilities of welding beyond traditional fusion methods. Friction welding uses rotational motion and axial pressure to generate heat, which softens the interface and forges a bond between the materials. Its advantages include strong, defect-free joints that do not require the use of filler. Its limitations are that it's restricted to rotational parts and requires very specialized equipment. Applications include drill bits, axle shafts, and turbine components. It's ideal for cylindrical parts where strength and reliability are paramount. Ultrasonic welding applies high-frequency vibration, typically 20 to 40 kHz, and pressure at the joint to disrupt surface films and enable intimate contact. This creates a solid-state bond without the need of melting. The vibratory energy is localized at the interface, so both temperatures remain low, which minimizes distortion and thermal damage to adjacent components. It excels with thin, non-ferrous metals like copper and aluminum, foils, and thermoplastics. In metals, it relies on plastic deformation and interfacial diffusion, while in plastics, it briefly softens the polymer at the fanning surfaces. Typical benefits include rapid cycle times, clean operations with no flux, filler, or fumes, and precise energy control via amplitude, time, and force settings. Common applications include wire terminations, battery terminals, microelectronic packages, catheter assemblies, and sealed housings in consumer electronics. When creating ultrasonic joints, you must focus on electrical resistance of the conductors, weld parameters, which are again amplitude, time, and force, and the anvil or sonotrode geometries. This summary table is designed to compare the different welding processes I have discussed and to support future process selection. One can start by matching the energy source and whether melting occurs to the part constraints. Fusion processes such as oxy-fuel and shielded metal arc welding offer strong metallurgical bonds with filler options, while solid-state processes, which are resistance, friction, and ultrasonic welds, avoid melting entirely. This reduces distortion and heat-affected changes to the parts. When selecting the appropriate welding process, consider joint type and geometry. Spot and seam welding are optimized for lap joints and sheet assemblies. Gas tungsten arc welding is ideal for thin sections and high integrity welds. Submerged arc welding and laser/electron beam welding suit thick sections or deep penetration with automation. You can then weigh production factors like deposition rate, positional capability, equipment complexity, and environmental factors. In practice, automotive bodies lean on resistance, spot, and seam welds. Aerospace use gas tungsten arc welding and laser/electron beam welds for their insane precision. Heavy industry adopts submerged arc welding for their throughput and integrity. Here are the references to all the sources I used to complete this assignment. Thank you for listening.